For a pendulum of length L with a mass m, we have gravity acting downward on the mass, giving us force, downward force of m times g, tension in the string. For an ideal pendulum, those are the only forces. For an ideal pendulum, we assume that theta is small enough that there is insignificant vertical motion of the pendulum, so that we have vertical equilibrium. But of course, with these two forces, we can't possibly have horizontal equilibrium unless the pendulum is in the vertical position, in which case the tension is straight up and mg is straight down. We also ignore centripetal force. So, if this is the equilibrium position, pendulum has length L, pulled back the displacement x, what's the net force? Well, if the angle is small, then there's not a significant difference, not a very significant difference, between the y component of the tension and the tension, since this angle here would be very small. In this case, well, we say small theta tells us that we have near vertical equilibrium then, and the magnitude of the tension is equal to the y component of the magnitude of the tension. And since we have vertical equilibrium, or very nearly so, that's equal to mg, so that the tension is equal to the weight of the pendulum. It follows then, from similar triangles, that the x component of the tension has magnitude mg sine theta, and of course that tension is directed back toward the origin. And that because if you do a force diagram, I didn't draw one, and you know how to do a force diagram for this situation. If you do a force diagram, you have just this force and this force, and the triangle you get when you analyze the tension, of course here is the diagram, has Tx here, T here, the tension T here on the hypotenuse. Here's the angle theta, so this tension must be equal to this tension times sine theta. So, and it's in the direction opposite x. So if x is positive, the force will be back toward equilibrium. If x is negative, the force will be positive, still back toward equilibrium. So, the x component of the tension is negative mg sine theta, and I'm a little bit imprecise about that. If theta is measured in this direction, then a theta in this direction would be negative and would give you a positive mg times the magnitude of the sine. So you can work that out. But we end up with the idea that the net force is negative mg times x over L, and that kind of glosses, that kind of fixes any error we made with the sign of the sine function, positive or negative sign. Because, as we can see, the force is always opposite to the displacement x from equilibrium. Okay, well, in that case, net force being mass times acceleration, and I've got to find myself a piece of white chalk because something got erased in handling the board. Ma equals the net force, and the net force is this, so that A being x double prime, we get mx double prime equals negative mg over L multiplied by x. From that, we conclude that x double prime is negative g over L. It's negative g over L times x. Divide through by the mass, you just end up with the negative g over L. Now, the solutions to this equation, we can't prove that these are the only solutions, but I'll simply tell you it's not difficult to prove that they're the only solutions. It's one of the things you do early in a differential equations course, but we can't assume that you're at that point. So, but it is easy to prove. First of all, you can prove just by substituting this function back into this equation. You take two derivatives and you end up with equality. okay, which verifies that this function satisfies the equation, and we actually do that here. It's very straightforward. I'm not going to read it to you. So x equals sine of square root of g over L, and I really didn't finish my statement. There is a solution. Now, it doesn't mean that it's the only solution. If, but, seems like I'm saying something here. Okay, yeah, well, what I'm saying here is if x equals a times the sine of omega t, where omega is the square root of g over L. Now what we have here then is just sine of omega t, with omega equals square root of g over L. Okay, but if x equals a times the sine of omega t instead of just sine of omega t, the function still satisfies this. If you substitute this for x on both sides, you're still going to have an a factor over here because it's just a constant. When you take derivatives, it remains constant. It remains a constant factor of what you get. And of course, a is going to just be a constant factor over here. When a divides out, you just end up, again, essentially with what you have here. Now, I say this also works if x equals a cosine of omega t, and that's equally easy to verify, so I'll leave it to you to verify that. Then I'll say it even works if x equals a cosine of omega t plus b sine of omega t. And you can easily verify that. Okay, it works for a cosine of omega t, it works for b sine of omega t. If you take two derivatives, you're still going to get the square root of g over L times x on both sides. Okay, and I'll just comment briefly on the reason that you have these two solutions, and it simply comes down to the fact that in the space of functions, the cosine of omega t and the sine of omega t are linearly independent. It's a linearly independent set of two variables, and also this is a second order differential equation. It's like if you have a first order differential equation like x prime equals something, when you integrate you get one arbitrary constant, your integration constant. To solve this, you're effectively integrating twice, giving you two arbitrary constants. That would be your a and your b. Now there's a little more to it than that. It's just making a plausible argument and relating this back to what you learned in linear algebra about functions and linear independence. Then I went on, I couldn't help myself, so you can ignore this if you want. I'm just saying that the set cosine of n pi t, where n is an integer, spans the space of differentiable functions. Now that's an infinite set because they're infinite integers. And an integer, not and integer, okay? And in fact, you don't need all the integers. All you need is the non-negative integers, and you still have a set that spans the space. But in this case, that set is linearly independent, so it's a basis for the space, meaning any differentiable function can be expressed as a sum of cosine functions, cosine of n pi t. Now that's not quite exactly true. You kind of need the sine functions too, or something similar, because you have to have something that's out of phase with this. And that goes well beyond anything we need to talk about here. But in case you're interested, that leads to a lot of very profound tools for analyzing functions, okay? Especially when you get to partial differential equations. Okay, so you're not going to have to worry about partial differential equations in your first 2 years. So it's something that becomes very powerful later, though.